Hi folks! The following video is our third and final one on radicals. I'll be discussing two new reactions known as allylic bromination and radical addition of HBr, and then I'll be discussing synthetic considerations involving radical reactions. The first reaction I want to discuss is known as allylic bromination. Allylic refers to the position adjacent to an alkene. Let's consider this alkene starting material and the different types of CH bonds present in it. There are three different types of CH bonds. The CH bonds of the sp2 hybridized carbons of the alkene, the allylic CH bonds that are at a position adjacent to the alkene, and then these other secondary carbon-hydrogen bonds that are not adjacent to the alkene. These three different types of CH bonds have very different bond strengths. Notice that the sp2 hybridized carbon-hydrogen bond is the strongest bond, meaning it's the hardest to break. And notice that the allylic CH bond is the weakest bond present, meaning it has the lowest bond dissociation energy. This means that this position is going to be most reactive in a radical reaction. Let's consider that allylic position participating in a hydrogen abstraction step with a radical. Here X is likely to be a bromine. The mechanism for this hydrogen abstraction step will have three curved arrows. From the X radical to a point in space, from the CH bond to the same point in space, and then from the CH bond to carbon. This hydrogen abstraction forms a new HX bond, and it forms a new radical at the allylic position. Notice that the unpaired electron of the radical is adjacent to the pi bond, so we have radical resonance stabilizing this radical. To draw the resonance structure, I would bring the radical down, and one of the pi bond electrons over to form a new pi bond, take the other electron from the pi bond and bring it to the far carbon. In the other resonance structure, the position of the pi bond and the radical have both moved. So let's imagine treating an alkene with Br2 in the presence of light. You might initially expect that this would proceed in a similar way to alkane halogenation, in that the weakest CH bond would break and the halogen would be added to that position. It turns out that that is not the major product if you just treat the alkene with Br2 in the presence of light. There's a competing reaction that's also observed, and this is that bromine can react with the alkene without the necessity of light. This leads to anti-addition of two bromines to generate a dihalide product. And this is observed as the major product if you have Br2 even in the presence of light. So this reaction, trying to install a bromine adjacent to an alkene, is not good enough. We have competing reactions that mean this would give us a poor yield. To prevent Br2 from adding to the alkene, we're going to need to keep the concentration of bromine low. And we'll do this using a new reagent called NBS instead of Br2. This will release just a little bit of Br2 at a time that will allow your radical reaction to proceed without getting that alkene addition that you don't want. NBS stands for N-bromosuccinimide. This is a 5-membered ring with a nitrogen, flanked by 2 carbonyls with a nitrogen-bromine bond. Upon treatment of NBS with light or heat, you can have a homolytic cleavage of the weakest bond in this molecule, the nitrogen-bromine bond. For the homolytic cleavage, you would take one electron from the bond and bring it to nitrogen, the other electron from the bond and bring it to bromine. This is going to form a nitrogen radical. This is resonance stabilized because the unpaired electron on nitrogen is adjacent to actually 2 pi bonds. And this reaction of NBS also forms a bromine radical. In the mechanism that I'm going to draw soon, this bromine radical is our propagating one, meaning it's going to show up in the propagation steps and be used and then reformed. Overall, to get the desired allylic bromination, breaking an allylic CH bond and installing a bromine at that position can be accomplished by treating an alkene starting material with NBS in the presence of light or heat. In the products of this reaction, a carbon-hydrogen bond at the allylic position has been broken, and this has been replaced by a bromine. Because this new position with the bromine added as a new chiral center, you would get two different stereochemistries of product, and in this case, these two products are enantiomers, making this product racemic. I'm going to draw out the mechanism for the allylic bromination reaction. I'm going to divide this into our initiation, propagation, and termination stages. In the initiation step of the mechanism, a homolytic cleavage will occur, which is helped by the presence of the light. The weakest bond is going to break, and this is present in NBS. I'll have a homolytic cleavage of the nitrogen-bromine bond, and this generates a nitrogen radical and the propagating radical, a bromine one. The first propagation step is a hydrogen abstraction. The bromine radical is going to break the weakest CH bond, which is adjacent to the alkene. I'll bring the bromine radical and one electron from the CH bond together, and take the other CH bond electron and bring it to carbon. This forms the resonance-stabilized allylic radical and HBr. The next step of the mechanism is a little bit strange, and it is not a radical reaction, and you don't need to know how to draw the curved arrow mechanism for it. In this next step of the mechanism, NBS starting material reacts with the HBr that was generated to form a nitrogen-hydrogen bond and Br2. So this is the step that creates a small concentration of Br2. This is essentially an acid-base reaction. The final propagation step is a halogen abstraction from that newly generated Br2 molecule. I would bring the carbon radical and one of the bromines together to generate a new bond, take the other electron from the bond and bring it to bromine. This forms the new carbon-bromine bond of the product and regenerates the bromine radical. On your own, just to check out our 3 propagation steps, try summing these together and notice that they sum to the net reaction, as propagation steps should. In the termination step of the mechanism, there are different possibilities. One is that 2 bromine radicals could couple together. I would bring those 2 unpaired electrons together, and this would form a new Br2 molecule. One complication that can occur with allylic bromination is that you can get a mixture of products due to resonance. Here I have an isopropyl substituted alkene being treated with NBS and light. I want to identify the weakest CH bond in the starting material. This is the one that's going to break and be replaced by a bromine in the product. In this molecule, the weakest CH bond is present at this tertiary position, where a radical generated here would be resonance stabilized. Without drawing out the whole mechanism, I want to imagine what radical would form if I do that hydrogen abstraction. If I break that tertiary CH bond, I would form the following tertiary radical. Because it's adjacent to an alkene, there's another resonance structure that I can get to. And in the other resonance structure, the alkene has moved and a primary radical is present. Both of these resonance contributors are important for predicting the products. Let's imagine the tertiary radical form undergoing the halogen abstraction, which adds a bromine to the position with the radical present. This would give us a tertiary alkyl halide product. But we also need to think about what if the primary radical resonance contributor underwent the halogen abstraction. This other resonance form would give a primary alkyl halide product instead. These two products are constitutional isomers of each other. When you're predicting products, you need to consider the fact that this allylic radical that you form is resonance stabilized, and you can add halogens at either radical site. I recommend 3 steps for predicting the products of allylic bromination reactions. The first is to identify the weakest CH bond, remove the allylic hydrogen atom, and draw resonance structures for the resulting radical. Then place a new bromine at each location that has a carbon radical present. Then analyze your products, see if any new chiral centers have formed, and then show stereochemistry. So let's consider the following alkene being treated with NBS and light. These are the reagents of an allylic bromination. I want to identify the allylic position. This is the one that's going to lose a hydrogen atom in the hydrogen abstraction step to generate a carbon radical. Step 1 is drawing that radical and its resonance structures. So I would initially break the CH bond to put a radical adjacent to the alkene, then draw the other resonance structure for this radical. Then I would draw the products where I place a bromine at each position that had a carbon radical present. And last, I need to identify if any new chiral centers have formed. In the molecule on the left, a new chiral center is present, whereas the molecule on the right is achiral. To show my final products, I would draw stereochemistry at the molecule that has the new chiral center. So I would draw 2 stereoisomers of that product, one with a bromine wedge, one with a bromine dash, and then I would draw my other achiral product as well. So if you were asked to predict the products, step 3 is really your final answer. Next, I want to talk about another type of reaction, which is radical addition of HBr to an alkene. Recall that we have 2 different regiochemistries for HBr addition to alkenes. If an alkene is treated with HBr by itself, Markovnikov addition occurs, where you first add the hydrogen to the less substituted carbon to make a carbocation, and then add the bromide in a second step. The net effect is that the bromine adds to the more substituted carbon. Alternatively, if the alkene is treated with HBr in the presence of ROR, an alkyl peroxide, anti-Markovnikov addition occurs instead, where the hydrogen adds to the more substituted position and bromine adds to the less substituted position. Now that you know about radicals, we can finally explain the mechanism for this anti-Markovnikov addition in the presence of the peroxide. Here I'll show the mechanism for this addition of HBr to an alkene in the presence of ROOR, and I'll divide the mechanism again into initiation, propagation, and termination steps. The first initiation step is a homolytic cleavage. The weakest bond in the reaction mixture is the oxygen-oxygen bond of the alkyl peroxide. This bond breaks homolytically in the first step of the mechanism. This generates 2 equivalents of an OR radical. This mechanism is a little different from the ones we've seen before, in that there is a second initiation step. This is reaction of the oxygen radical with HBr to generate a bromine radical. This occurs by a hydrogen abstraction step. So I bring the oxygen radical and 1 electron from the HBr bond together, take the other electron from that bond to bromine. This forms an OH bond and the bromine radical. What you're going to see is that it is the bromine radical that's the propagating one, meaning I'm going to use it in the first propagation step and reform it in the last propagation step. In the first propagation step, the bromine radical reacts with the alkene pi bond. in addition to the pi bond occurs. I'm going to take one electron from bromine and one electron from the pi bond together to form a new bond, take the other electron from the pi bond and bring it to the more substituted carbon of the pi bond. This addition step generates a new carbon-bromine bond at the less substituted carbon and makes a new radical at the more substituted carbon. In the second propagation step, a hydrogen abstraction occurs between the carbon radical reacting with another equivalent of HBr. I would bring the carbon radical and one electron from the HBr bond together, bring the other electron to bromine. The first two arrows coming together show the new carbon-hydrogen bond forming, and the third curved arrow with the electron going to bromine regenerates the bromine radical. So notice, like I mentioned, I used the bromine radical in the first step, and I reformed it in a later propagation step. You can also check that these propagation steps do sum to the overall reaction. In a termination step, two radicals will come together in a coupling reaction. One possibility is that two bromine radicals could come together. This would form a Br2 molecule. The regioselectivity of this reaction is dictated by the step in which you have the bromine radical adding to the pi bond. So let's imagine the bromine radical coming into this di-substituted alkene. If you add the bromine to the less substituted carbon, a more substituted tertiary radical would form. Or alternatively, you could imagine, what if you'd brought in the bromine to the more substituted carbon? In that case, a less substituted primary radical would form. Because tertiary radicals are more stable than primary ones, it is this tertiary radical that would be formed in this particular reaction. Let's compare the typical compared to the radical HBr addition reactions to an alkene, just looking at the key intermediate. In the case of regular HBr addition by the ionic mechanism, the proton adds to the less substituted carbon so that you make a more substituted tertiary carbocation intermediate in this case. In the radical mechanism, you're also thinking about making the most stable intermediate possible, but because it's a bromine that's adding to the pi bond first, the bromine gets added to the less substituted position, and you prioritize the stability and substitution of a radical intermediate instead. So in both the ionic and radical reactions, you're looking to form the most stable intermediate possible, and because the mechanisms are different, where you add the H versus the Br differs between these two reactions. Now let's consider the stereochemistry for the radical addition of HBr to an alkene. For this, let's consider a tri-substituted alkene reacting with HBr in the presence of ROR. I would start by drawing the product without any stereochemistry shown. This is anti-Markovnikov, so I've added the bromine to the less substituted carbon. Then you would want to check for new chiral centers. In this case, the carbon with the bromine added to it is a new chiral center. To show the stereochemistry of the product, you would want to draw two different stereoisomers. One where this bond to bromine at the new chiral center is a wedge, and one where this bond is a dash. These two stereoisomers arise because the bromine radical can add to the alkene from either above or below the alkene, which is planar. Now let's consider another example where we still have a tri-substituted alkene, but now two of the substituents are methyls and one is an ethyl. Here as well, anti-Markovnikov addition would occur, so the bromine would add to that less substituted position on the left. In this case, two new chiral centers have been generated. We'll need to consider the new stereochemistry at each of these chiral centers. And it turns out that 4 stereoisomers of product are formed. In one of these, the bromine added as a wedge, and a hydrogen that isn't shown added as a dash. In one of these, bromine added as a wedge, and the hydrogen not shown added as a wedge as well. In another, bromine added as a dash, and hydrogen added as a wedge, not shown. And in the last, bromine added as a dash, and hydrogen added as a dash, also not shown. First, the bromine radical could add from above or below the planar alkene. This would generate a carbon radical. That carbon radical is also planar, and then the hydrogen could add from either above or below that radical intermediate. For the remainder of the video, I'll talk about using radical reactions in synthesis. The radical bromination of an alkane is extremely useful. This is because this is the only reaction we've seen in the semester that can add a new substituent to an alkane. So let's imagine you wanted to add on to the following alkane. You could treat this with bromine in the presence of light. The radical bromination reaction is regioselective, and a bromine would be added to the most substituted position with a hydrogen present in the starting material, in this case generating a tertiary alkyl bromide. Once you have this bromine installed, you could either add a nucleophile to switch out the bromine for a different substituent in a substitution reaction, or you could treat the alkyl halide with a base to cause an elimination reaction. In this particular alkyl halide, there are 2 different types of beta positions, a methyl group compared to these 2 CH2 groups of the ring, and by choosing the size of your base carefully, you could form one of the alkenes shown. The radical bromination of an alkane is useful in converting between an alkane and an alkene. Earlier in the semester, we saw that you can convert an alkene into an alkane by treating the alkene with hydrogen in the presence of a metal catalyst like platinum. To go the other direction, you would treat the alkane with bromine in the presence of light to form an alkyl halide, and then you would treat that alkyl halide in a second step with a base to cause an elimination to form the final desired alkene product. So a radical reaction involving an alkane is our only way to convert an alkane into anything else. Today's video introduced a useful new method to add a functional group adjacent to a pi bond in a molecule. To do that, you would treat your alkene with NBS in the presence of light. This would add a new bromine at the allylic position adjacent to the pi bond. Here I'm not drawing stereochemistry, but know that you would have 2 different enantiomers of product because you do have a new chiral center. And now that you have an alkyl halide, you can go back to all of your old substitution and elimination reactions involving alkyl halides. So you could treat that alkyl halide with a nucleophile to add a new substituent adjacent to the pi bond. Here as well, you may have to worry about stereochemistry. Or alternatively, you could treat the alkyl halide with a base to cause an elimination reaction involving a beta position to form a new alkene. Because the original molecule had an alkene starting out, this new product has 2 alkenes adjacent to each other. As an example of this strategy at work, let's consider trying to convert cyclohexane into the following product, in which I have an alkene present that's new, as well as a new substituent that's adjacent to the alkene. I'll begin the synthesis by thinking backwards a step. So I don't know a way to install an SH group adjacent to an alkene, but I do know a way to install a bromine adjacent to an alkene. In order to convert a secondary alkyl bromide into a secondary carbon with an SH group present, you could treat the alkyl halide with SH-, a good nucleophile and weak base. This would cause the desired substitution reaction by an SN2 mechanism in this case. Now I need to go about making that allylic bromide intermediate. I'll start back at the cyclohexane starting material. The only reaction that we know for adding a substituent on this is radical halogenation. I will use Br2 in light because that's a more regioselective reaction than chlorination, so I use it much more regularly. This would form the bromocyclohexane product. To generate an alkene, you would treat this alkyl halide with a strong base, such as sodium hydride. This would cause an elimination reaction. Note that in this case, the size of the base doesn't matter. Then to close the gap, getting from cyclohexene to the bromo-substituted version, I would treat the alkene with NBS in the presence of light. Those are the reagent and conditions for the allylic bromination reaction. Okay, so to quickly summarize, this video talked about two new types of radical reactions: allylic bromination involving NBS, and radical addition of HBr to an alkene. This was a reaction we saw earlier in the semester, but we only just now had the tools needed to draw the mechanism for it. Toward the end of the video, I also talked about some strategies for using radical reactions in synthesis questions. That's it for this video. I will see you in class.